Thank you very much, Tino, for the introduction, and thanks to the organizing committee for inviting me. It has been really great pleasure to be here this week and also earlier in January, because the project or the topic that I will talk about is from a project which started with Tino Ullrich at about 5 years ago at another event like this, namely at a conference at the Hausdorff Institute, which was organized by Christoph. And it's somehow fitting that 5 years later, it's basically we're finishing it up while attending this program, and so the time in January with Gustavo helped a lot to bring this essentially to a closure, although it seems that whenever we think we're done, another interesting question comes up, and you know, every solved problem carries a new question. All right. So there are 5 papers listed here out of 6, and the first papers deal with the question whether the Haar system is an unconditional basis in spaces measuring smoothness. And of course there are many spaces measuring smoothness, but there's a standard or 2 standard scales, the scale of Besov spaces and the scale of Triebel-Lizorkin spaces. There are also other interesting scales like variation norm spaces, which do not fit into those cases. But so we are going to stick with those spaces. And although I think that probably most of you know exactly what I'm talking about, the definitions of these spaces, I put them up for you just for reference. So essentially what one does is one looks at an inhomogeneous Littlewood-Paley decomposition in dyadic frequencies, and then one weighs these with the smoothness parameter. So if you have frequency c about 2 to the k, you multiply by 2 to the ks, then you take either the little LQ of LP norm to get the scale of Besov space, or you take the LP of little LQ scale to get the scale of Triebel-Lizorkin spaces. The latter is defined for p less than infinity, and if p is equal to infinity, one would like, so first of all, if q is equal to 2, one would like to get the LP Sobolev spaces, and when p is equal to infinity, one would like to get a BMO version of this, and indeed there is a BMO type definition for p equal to infinity for all of these spaces, which is due to Fraser and Yarwood, and so if you know it, okay, and if you don't, it really doesn't matter much for the talk. So there would be other questions later where we drop the word unconditional from the problem. So we ask, is the Haar basis in an appropriate sense a Schauder basis, or a Schauder basis with various properties? And so we're going to discuss this a little later. All right. So just everybody probably knows what better than me what a Haar function is. So the Haar basis is so based on dyadic intervals, is one of 2 orthogonal systems which are associated to the set of dyadic intervals. One is the Walsh system, which is very close to the Fourier system, and one is the Haar system, which is very far away from the Fourier system, but it has lots of very nice, good properties in terms of localizing an operator. All right, so the typical Haar function is simply you take a dyadic interval, say of width 2 to the, well, here it's 2 to the minus j, and you say it has half frequency 2 to the j, and it's 1 on the left half of this interval and minus 1 on the right half. Okay, so these functions are normalized in L infinity. So if you renormalize them by multiplying by 2 to the j over 2, you get an orthonormal basis. And in order to complete that orthonormal basis, we would have to add the characteristic function of intervals of length 1. So you can either do this on the unit interval from 0 to 1, or you can do it on all of R, right? And so sometimes that makes a difference, and we're going to comment on that later. There is a version of this in d dimensions, and you don't really have to read that file. You can just accept that there is a version in d dimensions. So if you give me a unit cube, there's not just one Haar function, but there are 2 to the d minus 1 Haar functions associated to this cube, and then you build up a similar sort of wavelet structure. The Haar system is the first wavelet. It wasn't called wavelet when it was invented, neither it was called Haar function, so that's what we call it now. Basically, so those 2 to the d minus 1 Haar functions associated to each individual cubes are gotten by multiplying either characteristic functions or Haar functions in the various coordinates. And so then you get this Haar system. And so you could, for all that matters, just consider the case d equal to 1 to follow everything in this talk. Okay, so this is also about basis. So I'm not going to give you the formal functional analytic definitions of what a basis is. I rather say, given the Haar basis, we say what it means for the Haar basis to be a Schauder basis, an unconditional basis, etc., etc. All right. Now, first of all, this definition of basis, or in the first definition, it's actually a basic sequence, doesn't depend on the set of functions that we consider. Well, it does depend, of course, but it is not only dependent on the set, but it's actually dependent on the order in which we write out these functions. So we always need an enumeration. Okay, so we do an enumeration, and then for that enumeration, we say that this enumeration is a basic sequence if the orthogonal projections of the first n is defined on the span of this, the closure of the span of this basic sequence to the linear span of the first n of these functions are uniformly bounded. All right, and so then just by abstract nonsense, you see that for functions in the closure of the span, the Pn's will actually converge to the function in the norm under consideration. Okay, so now if in addition we know that that span, the closure of that span is the whole space, the span of U is dense in the function space, then we say that U is a Schauder basis. All right, now there are many enumerations, and so if we have a uniform bound over all enumerations, then we have unconditionality, because that's equivalent by saying, well, if we take any partial sum and you multiply randomly with plus or minus 1, you always have uniform bound. Then we say that the enumeration, but then also the full system, the Haar system, is an unconditional basis. So we have that the span is dense, and all equivalent to what I just said, all orthogonal projections to the spaces generated by finite subsets are uniformly bounded on the space. Okay, so and then there's a definition 4, which I just tell you what it is. You don't find it in any book, but it's kind of useful for our talk. So the Haar basis, think of the Haar basis defined in Rd, and we say it's a local basis if it is a Schauder base, the Schauder basis property only holds for functions which are compactly supported. Okay, so I give you a compact set, the functions are compactly supported, and then the projections that occur in the previous definitions have bounds which may depend on the compact set. So this is to essentially distinguish the Haar basis on the unit interval and the Haar basis in Rd. There might be or might not be a difference. All right. So just a few historical remarks. The Haar basis obviously was introduced by Haar as an orthonormal basis, and Schauder noticed that in the sense of our definition, and his definition, in fact, Haar system is a Schauder basis. So we can expand a function into, the orthogonal projection to the unit characteristic functions of unit intervals. That's the expectation operator associated to those unit intervals, plus an orthogonal expansion. Hj mu is the Haar function of width 2 to the minus j or frequency 2 to the j, and mu indicates the position of the Haar function. And so then we have convergence in LP, and it's basically, you know, it's nowadays this would be probably an exercise in a real analysis course. So what's important here are the conditional expectation operators, En, which are associated to the dyadic intervals of length 2 to the minus n. They naturally come up here. So if you sample all Haar functions of frequency less than or equal to 2 to the n, or maybe 2 to the n minus 1 or 2 to the n plus 1, but so up to a certain point, then these expectation operators come up. And if you take a difference of these expectation operators, so it's actually written that En plus 1 minus En is the orthogonal projection to the space generated by the Haar functions with Haar frequency 2 to the n. Okay, so there's sort of an outstanding result here mentioned by Villar. If you take the unit interval or equivalent to torus, this Haar system is actually a Schauder basis also on the Hardy space, which is an important result in the history of this development. Now, perhaps a really important result goes back to Marcinkiewicz, who showed that if p is strictly greater than 1 and less than infinity, then the Haar functions form an unconditional basis. All right. Now, that's really good news for people in applications. I mean, don't want to think about you know, the order in which you write things out. It's really bad news for people working in Fourier analysis, because many important problems, say like the multiplier problem, become completely trivial if you have an unconditional basis, right? If you have a basis but not an unconditional basis, then these problems might actually make sense. But for an unconditional basis, you take a multiplier, which is written down here. If that is a bounded function, then you have a trivial estimate in the instance of an unconditional basis. Now, Pelczynski showed that L1 cannot be embedded in any Banach space with an unconditional basis, no matter what that basis might be. All right, so L1 is always out for unconditionality. And so we'll wonder for the spaces that we're interested in here, namely the Besov and the Triebel-Lizorkin spaces, for which spaces is the Haar system a basic sequence, a Schauder basis, an unconditional basis, and does it matter whether we do a local problem or a global problem? There always is an obvious necessary condition. The Haar functions are quite rough, right? Almost, well, one derivative is almost in L1, it's a measure, but it's not better than that. Right? So the Haar functions must belong to the space, and so that severely restricts the smoothness parameter that comes up, namely S has to be less than 1 over P, and perhaps in one limiting case S might be 1 over P, but nothing much there. Also, if you think about our definitions, projection operators played a role, and they're all essentially self-adjoint. Okay, so if you have one estimate, they will also have some kind of dual estimate. If you think about that, it comes down to another necessary condition that, well, S is less than 1 over P, S is also greater minus 1 plus 1 over P. So there's a sort of a very small range of small positive S and small negative S where this is only interesting. Okay, and additional restrictions might come for cases with P less than 1 where you can use interpolation. I said here we often disregard the space P equal to infinity and Q, or those cases with P equal to infinity or Q equal to infinity, and simply because they are not separable. And so the Schwarz functions are not dense, and so we cannot have a basis, right? But we might have a basic sequence, so that question is still interesting. All right, so some references to previous work. So the first person who looked into this problem was Hans Triebel in the 70s, and then 5 years later, and so he proved that he looked at the Besov space and proved that the Haar system is an unconditional basis under a certain assumption. It was basically, if you remember, if you ignore the first term, d over p minus d, it's just when s is between 1 over p minus 1 and 1 over p. This was the necessary condition for p greater than 1 when we could use duality. All right, so he solved the problem, and he solved for the Besov problem in this range. You have an unconditional basis. Well, he solved the problem up to endpoint cases. There might still be something might be worth considering at the endpoint cases. Right, so the first condition there, d over p minus d, comes in if you allow values of p less than 1. Okay, we're going to have a picture in a moment. Right, so then there were many more results. So I put up a few names there. And I'm pretty sure that, you know, a good portion of the audience is not mentioned here and might feel offended right now, because of course wavelets come out of the Haar system and many people work on this type of question. But somehow nobody considered the space of Triebel-Lizorkin spaces. And I remember a very nice talk by Bourdeau in Oberwolfach, who gave for the more general wavelets a rather nice characterization in Triebel's, you know, in the sort of in the sense of Triebel's result for more general wavelets. And I was very young at the time, but dared to ask him afterwards, so what about Sobolev spaces? And I said, well, Sobolev spaces are harder and Besov spaces are already hard enough. That's what he said. Okay, but they're not so much harder as we know in harmonic analysis, so possibly you might need some singular integral theory, a maximal functional operator theory to extend things from Besov spaces to Triebel-Lizorkin spaces, and so you can see that implicitly, at least in Triebel's monograph, where he extended these results from Besov spaces to Triebel-Lizorkin spaces. And there's another range. It's essentially the same range as for the Besov spaces with 2 more conditions depending on Q. Okay? And so you can ask whether these are necessary, because he doesn't tell us whether they're necessary. So here's the picture that I mentioned, and this will come up a lot in the talk, slightly smaller maybe. So what we are picturing here is the parameter domain. There's this big figure, pentagon. In the interior of this pentagon, where S is graphed against 1 over p, in the interior, the Haar system is an unconditional basis for the Besov spaces. And in the smaller region, which is darker, the shaded region, the Haar system is an unconditional basis for the Triebel-Lizorkin spaces. And if I say the smaller region, I mean the interior of the smaller region. Okay? So what's perhaps left over there from Triebel's result is the region over here. Over here, what can we say there for the Triebel-Lizorkin spaces? And also, what can we say on the boundary of this figure? Right? So essentially, the focus of the last research was actually the boundary of that figure. Okay, now there's a digression here. So the way we started working together, there was a paper jointly with Chris in 2006, which had the goal to settle a similar question for many other assertions which show up in the books on function spaces. Lots of times a theorem depends on P and Q, and it's usually pretty easy to determine that it might be sharp in P, but perhaps not sharp in Q, but we were never told. So that is not to say that the Q dependence is always there or sometimes there. We just don't know. It depends on the particular problem. And so the goal of that research was to settle this problem, and the easiest operator, which is sort of can be considered here, is the maximal inequality due to Petre, which is a maximal inequality for the Littlewood-Paley. Oops, I'm sorry about that. For the Littlewood-Paley operators acting on a sequence. So if we perturb this by h, where h is less than 2 to the minus k, we don't change it much because we stay in the same sort of uncertainty region, but if you perturb it more, then we have to damp the perturbation, and the question is, how is this perturbation damped? Does it, well, if n is greater than d over p, it works, but it also has to be greater than d over q, according to Petre, and the question whether this is needed, and the answer is that it is needed, and there was a probabilistic construction which involves lots of frequency in this paper with Christ, and it says, yeah, you really need it, and there's accordingly many other problems in the book where it's also needed, but it's not actually so easy to determine whether, say, the Petre maximum function used in proofs is actually essential for the proof or not. So given a problem like our problem, we had to determine whether certain structures are really essential for the proof, or whether we could somehow adapt this counterexample. Fk. Any Fk is a temper distribution. But the pk, remember, localizes to annuli. In fact, annuli are not important for this result. It's only important that they're localized to balls of diameter 2 to the k.
This is not pk of a single F.
It's the essential, the issue here really comes up if you have different pks. Okay, and in fact, the pks could be sparse. So many of the fks could be 0, right? And the question is, and you always have a counterexample. It never works. Take an infinite sequence of k's. This inequality never works unless you have the additional restriction on q. The restriction on p is sort of like maximal operator with respect to translation. It's something really easy to check, but the condition on q combines many scales.
It seems it makes no difference whether you write f or k. The pk's are anyway disjoint pieces of the function.
Yeah, doesn't make. Well, it makes a difference if we use the definition over there, but I just told you that the pk's could actually be localizing to balls rather than annuli, and then it would make a difference.
Okay, yeah.
Right, okay. Right, so the outcome of this, our discussion, Tino and I had this idea, well, this might work, and it took us a while to figure out that it did work, but it does work, and so the outcome here is that the Haar system is an unconditional basis if and only if the conditions mentioned in Triebel's book hold. So if we're in this shaded region. And the proof also shows that outside the region of unconditionality, if we were to define the Triebel-Lizorkin space by the dyadic model of Littlewood-Paley functions, namely the martingale differences, you get a different space. Right? So it's not quite the same as unconditionality. It's a little weaker, but that's also disproved outside the region of unconditionality. Any question? All right. So then the next question was, well, we have disproved that it's an unconditional basis. Let's also disprove that it is a Schauder basis, and according to that slide, we failed because it came out that we actually could prove a Schauder basis, and at that time we had teamed up with Gustavo. So all of this, I've said it on the first slide, but I may not have actually said it. All of this is joint work with Gustavo Garrigós and Tino Ullrich in the audience.
Excuse me, just a question. If you replace Haar wavelet by Whooper wavelet, this limitation on Q becomes irrelevant?
If you replace Haar wavelets by C infinity wavelets, the limitation becomes irrelevant. If you replace them by sort of spline wavelets, there are students working on the subject. Yeah. Right, so it's So certainly there should be some theorems in between the infinity wavelets and right now. So there are ranges given here. These ranges basically correspond to the big pentagon that we had, right? and well, to the interior of that pentagon. But the theorem doesn't make sense because I didn't tell you what the enumeration was. We know already for some enumerations it doesn't work, or no, it doesn't work uniformly in all enumerations. So we have to talk about enumerations. So how do we enumerate the Haar system? That's very easy on the unit interval. You start with low frequencies, go from left to right, then we go next and next and next. So how do you do this in Rn? You cannot go from left to right because there are too many to enumerate at a fixed frequency scale. So you have to make up some kind of natural enumeration which somehow models the enumeration, the standard lexicographic order. You cannot do it globally. So for Besov spaces, this result is also true, but we already know where we have unconditionality even, right? So it's kind of irrelevant. So admissibility means roughly mimicking the lexicographic order for Haar functions on the unit interval. One has to be careful, but I do not care to elaborate why. And so in the end, we come up with the following definition. An enumeration is admissible if you have the following situation. So you take two functions in your enumeration, un and un prime. They are supported in some fixed dilate of a dyadic unit cube located somewhere in Rn. And if the support of un is greater than a fixed constant times the support of un prime, then the n becomes before the n prime. So it's essentially locally, think of locally what the lexicographic order is doing. And it's a rather easy exercise to see that you can do this by starting at the unit group and sort of going slowly to infinity. You can do that, right? So that's a natural thing to do. All right. Now, there are also, so let me just say just a little bit about the proof. So the natural object is in this proof is always the expectation operator, which is not in our analysis bounded by the Petrel maximum function, because it were we would run into problems, as I said before. Right, so what we prove a uniform bound for the expectation operators, and the way we prove it, we compare the expectation operator with the non-dyadic one, with the standard one where we localize in Fourier space to a ball of frequency radius 2 to the n. And it turns out that the difference is actually better. It's all about the difference. And the difference is better for fixed S. We can choose on the right-hand side the largest Triebel-Lizorkin spaces, and on the left-hand side, I can say the smallest, but essentially the smallest Besov space. I mean, any Besov space where R can go to 0. Okay, so that's really nice, and so that gives us a lot of flexibility. Right? So that theorem can't be very hard because it's a better estimate than you might shoot for, but that inequality fails at the endpoint cases. Okay, so I'm supposed to tell you about the endpoints. And how many slides do we have for the endpoint cases? Well, at least 5, right? Because it's a pentagon. And well, we have a little more because we say something more, but so we have 5 endpoint cases, and we want to discuss this, and so I'm going to go counterclockwise. It's almost, if counterclockwise is sort of an increase in difficulty. So we start with a very easy case. The very easy case is the case where S is equal to 1 over P, and nothing much happens there because simply the Haar functions do not belong to the spaces. Okay, so there's nothing to do. They do not belong to the Triebel-Lizorkin space for any Q, but for the Besov space there is a difference. There's actually the case Q equal to infinity, then the Haar functions belong to the Besov space. Something might happening there, and what happens is indeed the conditional expectation operators are uniformly bounded on that one Besov space. So we have a positive result. Therefore, we also have some kind of basic sequence result if we, yeah, but I don't care to go into it right now. So there's something, and we'll say more about that a little later. The next region will be the region where P is equal to infinity and the S is negative. We go down. So the Triebel spaces pose difficulties because our usual definition doesn't work anymore. We have this kind of BMO type definition. But there's one nice thing here. Let me just show this to you with a pointer. This vertical line in our problem is dual to that line. So once we are in the range of duality, so PQ between 1 and infinity, since obviously by the previous result we can prove something here, we should be able to prove something there by duality. Okay, so there are some other indices where duality doesn't work, but we still are able to prove those things. So first of all, the conditional expectations operators are bounded on the Besov spaces. So here I want to make sure that I get this right. So in the open interval, so the Q equal to infinity was already handled. The last slide, S equal to -1, that's a bad point. The operators are uniformly bounded, this is what I just said, on B S infinity infinity. And in the Triebel space, they're actually uniformly bounded even up to S equal to 0 on the space Fs infinity Q. Okay, so that's also, that one has to show this, but essentially can be very hard because it's dual to something that we already know. The next endpoint case is perhaps slightly more interesting. But this one is dual to that one, right? And lots of things did not happen there. Right? So whenever it's dual, and we had already disproved the range where things go wrong, things will go wrong also on the left order. But not everything can be proved by duality. So what can be proved by duality? U is not a basic sequence on FSPQ for P greater than 1 and Q greater than 1 and the B spaces. And so we managed to show it also goes wrong for Q greater than 0. Okay, maybe not surprising. The Schauder basis in RD fails for, well, we have to say what it means, right? We had this admissibility condition. At least there's some admissible U that can be constructed that the Schauder basis property fails for any Q. All right? Okay, so maybe it's an artifact of RD versus the local case. We could use the unit interval, or we could ask the question about the local Schauder basis. And suddenly there's a positive result. When the index Q is less than or equal to 1, it works. Okay? And we cannot obtain this by duality from anything. So we have to prove it. Okay? So that's an interesting feature here, that the local result is very different from the global result. Right? So that's something to keep in mind. In that positive result, unconditionality fails. In fact, I will not have to repeat this. Unconditionality will mostly fail, or maybe always fail, on the boundary. So here unconditionality fails. All right, so now we have two cases left. The case where P is less than 1, where both P is less than 1. There's the vertical case where S is equal to 1, and then there's a case where we go up. And these cases are much more interesting. So what do we have? So let's do a P less than 1 and S between 0 and 1 on this line. This depends on the dimension, the slope of this line. So this is when D is 1, this goes straight up, but it's sort of broken line. It's a real pentagon in dimensions D greater than or equal to 2. And so if you take the Triebel-Lizorkin spaces in the case where we have a chance for a Schauder basis, the admissible U will always be a Schauder basis. So we have to prove an estimate. It's an estimate in Triebel-Lizorkin spaces. It's some kind of maximal operator, singular integral operator type estimate that one has to prove, obviously. So still, for Q equal to infinity, it's a basis sequence. Okay, so the Besov spaces are always easier than the Triebel-Lizorkin spaces, right? Because normally we think we have an operator on Besov spaces. We just have to check on dyadic frequency scale, and the putting together is sort of taken care by itself. But here it's kind of upside down. Suddenly the results for the Besov spaces are worse than the results for the Triebel-Lizorkin spaces. Okay, in fact, all admissible shorter bases are basic sequence on BSPQ if and only if Q is equal to P, and that's exactly the only case that's already taken care of in the F scale, because then the two coincide. Right? But again, this is actually an artifact of RD versus the local thing. If we ask the local question, it changes. All admissible U are local shorter bases, or you could formulate the appropriate analog on the unit interval on BSPQ on that line if and only if Q is less than or equal to P. There's a small range from 0 to P where it is a shorter basis. So the uniform boundedness actually fails for Q greater than P. So in all cases, as was indicated before, HD is not an unconditional basis. That last positive result here also has been obtained by Peter Oswald. So one thing about this, I said here the uniform boundedness of the EN fails. That doesn't mean that the EN are unbounded. They're unbounded in N, but they're as individual operators may be bounded, and so therefore, in the workshop on approximation theory, it makes sense to quantify this. What is actually the right bound? Right? So we can do that. And so here is we quantify the bound and we quantify the localization. So we take a large cube, diameter of the cube is greater than 1. Okay, and so we define an operator norm which is dependent on this large cube. It's simply the operator norm of the operator with the additional restriction that the support of the function is supported in that large cube. Okay, and then we would like to trace the norm independence of that parameter and in terms of the parameter n. And so if we are in this Besov case, the Besov case is now the interesting one. Triebel case, everything is bounded. On that line, over here, on that line for P less than 1, that endpoint line, for cubes of side lengths greater than 1, the operator norm depends rather badly on n and on the cube. If the cube goes to infinity, I'm assuming now that Q is greater than P, which is the region of where we do not have uniform boundedness, and this is exactly how it blows up. Right? When the cube goes to infinity, in Rn it fails, but for large cubes, we can measure it precisely in terms of the diameter of the cube, or the measure of the cube, and the frequency parameter. So the result, the example is kind of what is it? So in that cube, you draw points which have distance 2 to the minus n, and then for each point, you take a different Littlewood-Paley scale, a local Littlewood-Paley scale. You think of an L1 function, L1 normalized function, but it gets, for each point it gets thinner and thinner and thinner. Okay, and so that would be the counter example. So maybe I should say more about that. I'll go to the last line. So Tino, I have how much?
Still 5 minutes plus.
6 according to my time. Okay. So there's the case S equal to 1. That's a really interesting case. The ends are certainly uniformly bounded on F1PQ, S equal to 1. P is less than 1 in that range, if and only if Q is less than or equal to 2. Okay, so that suggests some relevance of Littlewood-Paley theory. Littlewood-Paley theory shouldn't have a place in the Haar, for the Haar functions, right? But it's there, and it's sharp. For the Besov cases, there's a similar theorem, but the Q has to be less than or equal to P. Okay, so that shows that the Haar system is a basic sequence of those spaces. But there's bad news: the span of the Haar functions is not dense. So we do not have the shorter basis property. And so we use an example which goes back to Triebel used it in the region above the line. Above the line, the ENs still have, they are not uniformly bounded. So we show that they're not uniformly bounded, but they are bounded as individual operators in some extended region, which I didn't draw here. Okay, but that example actually works. If one pushes it to s equal to 1, that example can be made to work. And Oswald also observed that this example can be pushed to the case s equal to 1. So the outcome there is that there are Schwartz functions for which, even Schwartz functions, for which the expectation operators do not converge in the norm when s is equal to 1. So that actually means that the span HD is not dense on this basis, right? Because if you know that the ENs are uniformly bounded, then you can disprove the density of the span by a little argument, little standard argument. However, if we did not know that the ENs are uniformly bounded, then we could not disprove that the span is not dense. We could not disprove that the span is dense. We could not prove that the span is dense. All right. Okay. But here's another quantitative observation. I would have liked to put the Q in there, the Q for large cubes. What happens for large cubes? So for the F spaces, the large cubes never matter. But the nice thing here in this example, for the Besov spaces, they do not matter either. Okay, they only matter for this other region. So I just omit them. It's uniform in all cubes, so it's also true in Rn. And now if we are in the range outside the one on the previous scale, namely for the S spaces if Q is greater than 2, and for the V spaces if Q is greater than P, then the operator norms of the EN should blow up, and we determine how they blow up. They blow up like this n to the 1 over P minus 1 over Q. So radically different behavior than in the previous example where they blew up exponentially. Here they just blow up a little bit. Okay, and they blow up. So the example, the more interesting example is probably one for the S spaces. So you use some kind of Lachinary series here, and you randomize it. So the randomization, somehow the set doesn't have any place in the Haar function theory, but it works. That type of example. So here's a little question that we cannot answer. What can we actually say about the density of the Haar system in those examples? Because we cannot longer use the uniform boundedness to disprove in the previous observation on the non-convergence of ENF for some Schwartz functions. We cannot longer deduce the failure of density. So that's it could be that there is a nicer approximation, right, than just EN. But we don't know what that nice approximation should be in the context. So something to work on. Right. So I guess I'm almost out of time, but I'd just like to mention a little side project here that we have. Coming back to the first slide, we have the difference between the regions of unconditionality and conditional basis property. And so I would like to focus on the lower triangle and this upper region here. And for simplicity, simplicity means that we haven't really considered the case p less than 1. So right now, let's just consider the case p greater than 1. Let's consider this region. So if we have a conditional basis, but which is not an unconditional basis, the multiplier problem makes sense. Right? So for every hj mu, we take the expansion, and we can multiply with m of j mu. And the most natural case to study first, well, particularly given the examples that come up, are multipliers which do not depend on the position, but just on the frequency. Okay, so that would be m of j. So what can we say about those multipliers? When does such an operator, multiplier operator, define a bounded operator on the Triebel-Lizorkin question? So what are the conditions? It turns out that variation norms come in. Okay, so we have the V u is a parameter between 1 and infinity. U equal to 1 corresponds to the standard condition of bounded variation. U equal to infinity essentially corresponds to L infinity, and so there's a VU variation in between, which is nowadays quite popular in analysis. If you have a Schauder basis, you can always deduce an easy multiplier theorem using the one variation, the standard variation. The question is, can you do better? And here's a theorem that tells you that you can do better. So the condition is that the U parameter satisfies 1 over U is greater than S minus 1 over Q, and that is essentially sharp up to endpoints. We don't know when we write equality what happens with equality. The examples in the paper with Tino on unconditionality was quantified there. It was really said, what do the operator norms do? They show that this theorem is sharp, and the example is essentially characteristic functions which have gaps, like any characteristic function which is supported on the even natural numbers. Well, so we could have larger gaps, it doesn't really matter. And if one computes the VU variation for those characteristic functions, it's essentially the cardinality over U, and one compares the previous counterexamples, uses that the theorem is sharp. All right, so I would like to stop here. Thanks for your attention.
Well, thanks, Andreas, for the presentation. So are there any questions?
Did you consider what can be called like hyperbolic Haar multivariate basis or system? That means the tensor product of univariate.
I understand it's a very interesting question, but we did not consider it yet.
Do you have any information about the behavior of the constants at this grade level when you go to the boundary, how they explode, or I guess they will explode, these unconditionality constants? I understood that you are having a statement for every point in the interior, there is some finite constant.
Well, it's not the unconditionality constant that we consider, because the examples are not in terms of the cardinality of the set, but it's rather the cardinality of the frequency set which disproves this. And then if we replace by the usual unconditionality constant by the cardinality of the frequency set, then the answer is yes. In fact, unconditionality fails at the boundary. And there's an interesting phenomenon that cardinality plays much more, in those triangles, the little triangles up and down. In the interior of this triangle, the counterexample depends roughly on the cardinality of the set, or suitable sets, I should say, while at the boundary they depend on sorts of other things like density considerations and so on. And so you can trace we did not write down the precise constant, but you can trace them through the proof and to get some information.
There was a question over there. So one last question and short answer.
Me or?
I don't know.
No, you go ahead. Yeah, I'll talk a lot in a minute. Yeah.
Okay, Sinan.
Okay, so it's a basic question. Actually, you ruled out the cases where Haar doesn't belong to the space, but a similar situation arises in C01, where you can have a Haar expansion, but the function is not in the space. So is there an analogous case here that?
Right. So I said in the beginning that there are lots of other interesting function spaces that do not fit into those cases. C01 does not fit into.
It does not, but
And
in the
it's
cases
certainly-
where you ruled out the possibility because Haar doesn't belong to the space, is there any case where this might have something
So
similar?
you might.
In the
When there's a larger space, of course,
Yeah.
where everything makes sense, and therefore it makes sense in
that's
C01,
right. Yeah,
right?
that's
So-
exactly what I'm saying.
And I'm sure that one can construct situations like that for endpoint cases, but I haven't systematically looked into it.
So it's a possibility.
Yes, so we should stop here and